It's great to be here. Thank you for inviting me. So I'm going to talk about a pretty broad range of topics here today. So first I'll talk about our work on the discovery of Gaia BH1. And then I'll talk to you a little bit about a possible environment where massive black holes that are been detected by LIGO can form. In particular, I'm going to suggest that they might form in the outskirts of spiral galaxies, that is, in the outer H1 disks of spiral galaxies that have relatively low metal content. And finally, I'll talk to you about our recent work on the detection or constraints that we now have on a possible primordial black hole or dark matter subhalo near the sun, about a kiloparsec from the sun, that we have characterized from pulsar timing line-of-sight accelerations. So, of course, the summer of 2022 was a very exciting time for many of us, with the Gaia DR3 data release that gave us phase space information for about 1 billion stars, average radial velocities. In particular, it was very helpful for topics in this conference. Particularly was the release of binary parameters for a substantial number of sources here. And Gaia certainly delivered on its promise. Most of the sources that we knew about previously were in black hole X-ray binaries. As you see here, these are at low orbital periods, but with the release of DR3 data, the first discovery of Gaia BH1 on a half-year orbit, and then this continued with discoveries of Gaia BH2 and the record holder Gaia BH3, nearly 30 solar mass orbit on a 30 solar mass star on an 11-year orbit. So these are really non-interacting black holes on very, very wide orbits that are quite distinct from the previous demographics of black holes in binary systems. So I'll talk to you a little bit about our search for a stellar mass black hole from the analysis of Gaia DR3 data. And I'll go through how we thought about it. And of course, Karim did a similar search. And I want to acknowledge Karim got to the finish line before us, a couple of weeks before us, and had a more extensive RV follow-up than we did. But let me tell you how we thought about it. This is our ADQL query. So we go through the non-single stars catalog, which has about 200,000 binary systems with orbital parameters. And, you know, we know that there can be errors in the astrometric fits, and we're looking now for dark companions. So we want to select a relatively large secondary mass that is comfortably above the black hole limit. So we selected for secondary masses larger than 5 solar masses, and we're looking for dark companions, so we remove double-lined spectroscopic binaries. And again, because we want to test the Gaia solutions, we know we're going to have to do radial velocity follow-up. So we selected for relatively bright sources to allow for easy follow-up. And we're looking for things that are not contributing any light. Okay, so we required that these sources are within half a magnitude of the Gaia main sequence. And we want to make sure that we're looking for things that are significant. So we selected for sources with at least 10 radial velocity points, significance more than 5. And finally, we want to exclude eclipsing binaries. So we exclude any sources that show variability in the tests light curves. Now that leaves us with about a dozen compelling candidates at this point. The most interesting of which is the object that is now known as Gaia BH1 for a number of reasons. The other sources have also been followed up and will be discussed in a forthcoming paper by Josh Simon. So this is, prior to our getting any radial velocity follow-up. Okay, this is the reason why we thought Gaia BH1 is the most compelling source of the set that we had looked at. And this is why we decided to focus on our radial velocity follow-up on that source. So you can see here in the red, we've marked the object that's now known as Gaia BH1 on the Gaia main sequence. It lies very close to the Gaia main sequence. And here we've retrieved all the available photometry, and we fit the observed spectral energy distribution, and it is fit very well by the light from a single sun-like star. And you can add additional components, and they do not improve the fit relative to the fit from a single sun-like star. Okay, so at this point, we were pretty convinced that we had what was very likely a black hole candidate, and we started getting radial velocities. This is an example of one of our spectra from Magellan compared to a G-type star, and we continued to get radial velocities for about 4 months with a number of facilities. And this is, important because the astrometric orbit for the source is really at the edge of companion masses in DR3. So the RV follow-up was essential. Now, of course, we also have access to the astrometry, the Philaeus parameters, along with the eccentricity, specify an orbit on the sky. So you see the samples, number of random samples here drawn in the blue, and the black is the best fit orbit. But we also want to see what the RV-only fits give us. Okay, so the top panel here is showing our fits using only our data set. And I want to emphasize that our data set is completely independent of Kareem's, and I'll talk about the advantages of having both data sets. So the top panel is our data set only. And you can see that in contrast to the bottom panel where we've included the data set from Kareem's paper, the most significant difference is that, with Kareem's data, he was able to constrain the apocenter of the orbit, and his RV follow-up is substantially more extensive than ours. But neither data set alone gives you a unimodal period. And the advantage of having both data sets is that you get a unimodal period without using any information from the Gaia astrometry. So these are our posterior distributions for the orbital parameters using just our own RV data set. And overall, the fits are pretty good, except for there's significant uncertainties here for the semi-amplitude because we missed the apocenter of the orbit. If we include all available RV data, we have a much tighter constraint on all of these parameters, particularly the semi-amplitude. Now, of course, we also have access to the reported astrometric parameters, the best fit parameters, and the various matrix from DR3. Okay, so we can carry out fits that simultaneously fit both the RV data and the Gaia astrometry. And that's what's shown here in this figure. In this case, using our RV data alone and fitting jointly to our RV data and the Gaia astrometry, we get a secondary mass of about 11 solar masses with an uncertainty of roughly about 1 solar mass. If we include all available RV data, that is, include Kareem's RV data and do a joint fit to the Gaia astrometry, this now gives us a somewhat lower mass of about 9 solar masses and correspondingly lower uncertainties. Now, one point I think that's worth noting is, this again I think is an advantage of including all of the available radial velocity data here. So this is showing the fits using the radial velocities and the fits using the Gaia astrometry. Okay, and our chi-squareds from our RV fits show that the velocity uncertainties have not been underestimated, but you can see that in general, aside from the eccentricity, a number of the derived parameters are somewhat discrepant at about the 2 sigma level. Now, it's important that I point out this is just pertaining to the specific, the details of the orbital parameters. Both the RV fits and the Gaia astrometry independently show that this is a black hole of mass of order 10 solar masses on a long period orbit. But I think it's pretty clear that the Gaia errors have been underestimated by about a factor of 2. So, a lot of exciting things happened that summer. One, of course, was the discovery of Gaia BH1. I also accepted a new job and moved to Huntsville. And finally, at that time, I had a Twitter account. I don't now because various reasons. But I was never active on Twitter. I had like a total of maybe 10 followers. But shortly after our paper came out, I happened to open my Twitter account one day, and this guy, Chris Hadfield, he's a Canadian astronaut, and he sang the song Space Oddity, floating around on the International Space Station. I highly recommend that. It's not an easy song to sing, whether you're on Earth or out there. And he happened to tweet about our results, so suddenly there was a lot of activity on my Twitter. All right, so I'm going to move on now to talking a little bit about some earlier work I did in trying to understand the host galaxies of the really massive black holes that were detected by LIGO. So we're talking about masses, really at the extreme edge, about as massive or more massive than Gaia BH3. So it's relatively well known that massive black holes form more easily in regions of low metallicity, because the winds are much weaker in those environments, which allow the star to retain more of its progenitor mass before it collapses. Now, for this reason, dwarf galaxies have been suggested as potential host galaxies for LIGO sources. They have low metallicity. But what I want to point out is that intragalactic environment can also matter. And so this is, motivated, my perspective here is motivated by the fact that I've done quite a bit of work on the outer H1 disks of spirals. So this is an image from Frank Beguil's paper that is showing the H1 disk of M83. The green here is the H1 map, and on the top you see the FUV image. So this thing is huge, by the way. The diameter of M83's H1 disk is about 80 kiloparsec, so much, much larger than the diameter of the stellar disk. And you see that the H1 and the FUV are correlated on the outskirts of M83. Now, the metallicities in outer disks are pretty low. Okay, but what do I mean by outer disk? I mean beyond the optical radius, beyond R25, where the B surface brightness in the B band drops below 25th magnitude. Okay, so you see, for example, this is in M101, and these have been studied for the last 2 decades now. Okay, typical metallicities in outer disks of spiral galaxies in the local volume are about 1/10 solar. Okay, so roughly similar to what you find in dwarf galaxies. Star formation rates are also roughly similar. Okay, so I think this is a reasonable question that we can ask. Can massive black holes form in galactic outskirts? And we're now going to come up with a very simple, highly approximate model to see if we can make some progress in answering this question. So here I'm adopting a mass efficiency, or fraction of mass, that forms black holes as a function of metallicity from some earlier work, and you see that this is increasing, right, at low metallicity. And now, for a given population that is either dwarf galaxies or outer H1 disks, we can calculate a merger rate and compare to some observations. Right, so we have this mass efficiency term. We can get some typical star formation rates. We have some average metallicities. This is the merging fraction that incorporates a delay time distribution. And here we can consider the demographics of H1, of say the H1 mass function, or of dwarf galaxies, and then you integrate, okay, over that population. And this is not making any assumptions about the specific detector network, the volume that it's sensitive to, so you need to normalize by that. At that time, this gave that reference volume would have given a order unity to a few events per year from binary black holes in outer H1 disks. So this is, of course, a very simple model. So let's see if we can do something that's more observationally motivated. So if these things are really forming binary black holes in the outskirts, there should also be supernovae in the outskirts. So let's see if we can, whether that gives us any additional insight. So what we've done here, we've gone through the Lick Observatory supernova search, which is, at that time, was the largest homogeneous sample of nearby supernovae. So this is showing the histogram of the total number of supernovae as a function of stellar mass, and in the outskirts. Okay, so if you consider dwarf galaxies, there are things that are order 10⁹ solar masses or below. The number in the outskirts is roughly similar. Okay, number of supernovae in the outskirts is roughly similar to what you have in dwarf galaxies. For this sample, okay, there are about 100 supernovae beyond R25. Okay, this is the number of supernovae as a function of galactocentric radius. And there are a total of about 700 supernovae in this sample. And we looked at the relative numbers, the types of supernovae here, core collapse supernovae and type 1a. Their ratios are roughly comparable between dwarf galaxies and what you find in the outskirts of spirals. Okay, so the rates of core collapse supernovae that may form LIGOs binary black holes in outer disks and in dwarf galaxies, they're roughly similar. There's the volumetric rate. There are more dwarf galaxies, so they are slightly larger, but the uncertainties here are also significant. So I think this is an area that deserves more research. And I'm excited to see what Gaia DR4 particularly will tell us about the formation of massive black holes in the outskirts of the Milky Way. Okay, so in the remaining time, I'm going to switch gears a little bit and tell you about our work on the detection or constraint, if you like, on an object that is either a dark matter subhalo or a primordial black hole that we found from pulsar timing accelerations. So let me give you a little bit of background on this. So what has been done traditionally in galactic dynamics is we have estimated accelerations by modeling a snapshot in time of the positions and speeds of stars under certain simplifying assumptions, particularly the assumption of equilibrium, which we know is not accurate for galaxies like the Milky Way. The Milky Way is in a state of disarray, it's in a state of disequilibrium. Okay, so that assumption leads to inaccurate results. We know about lots of independent lines of evidence that show that our galaxy is highly perturbed. This is from analysis of SDSS data that shows an asymmetry in the north-south star count, suggesting that our galaxy has been perturbed by a dwarf galaxy. This is the so-called Gaia-Enceladus merger that is believed to have shaped the disk of our galaxy. So what we're trying to do is we're trying to move beyond phase space measurements to, honest to goodness, acceleration measurements that are derived from a change in some quantity. And we have developed several different techniques to do this, and I'll only talk to you about our work on pulsar timing that's resulted in this recent detection. So very briefly, the idea here is that you can measure the times of arrivals of these pulsars very, very precisely. And this is the pulse profile shown in the bottom here. Okay, by getting lots and lots of these times of arrivals, you can average them to produce this type of pulse profile. That's an example of a slow pulsar. This is what's called a millisecond pulsar that's been hundreds of times per second. And these are the best timed pulsars, and we were able to use them effectively as galactic accelerometers by looking at the change in the orbital period for pairs of millisecond pulsars. So here's the basic idea here. So the quantity on the left-hand side is the observed time rate of change of the binary period. This is what we get from Nanograv and other pulsar timing facilities. The terms on the right are the physical mechanisms that lead to that change. The first term is due to the fact that these stars live in the galactic potential. Therefore, they must accelerate. They don't have a choice. The second term is due to the so-called Shklovsky effect, which is an apparent orbital change due to the pulsar's transverse motion. You can calculate that if you have the proper motion mu and the distance d. And this third term is the general relativistic orbital decay, which you can calculate if you know the masses and the eccentricities, which we do from pulsar timing. Okay, so what you see is that you know everything, okay, on the right-hand side, and so you can isolate and rigorously solve for the galactic acceleration. So we did this for the first time in 2021, and this is the top panel here is the posterior distribution of what's known as the Oort limit. This is the total midplane density of material in the galaxy, and you can see that it's well constrained to about 3 sigma. Okay. At that time, we were not able to constrain the local dark matter density, but more recently, this was our first attempt to constrain the local dark matter density. The errors were very large compared to kinematics, but more recently we have been able to do that. I'll just point out that one of the advantages of this way of doing things is that you can see evidence for disequilibrium in the galaxy directly in the pulsar accelerations. Okay, so this is showing the pulsar accelerations below the disk, close to the disk midplane, and above the disk. And you see that they're highly asymmetric, right? And that's a signature, okay? When the acceleration profile in a galaxy is highly asymmetric, that's a signature that the galaxy is interacting. And the same is true as a function of azimuth, and you can show this differently here. These are the line of sight accelerations above and below the disk. The gray shaded region is showing the errors in the pulsar timing measurements compared to a very old simulation that I did at the Sagittarius dwarf interacting with the Milky Way shown in the blue. So again, you see that the acceleration profile is highly asymmetric. And one last thing that I will point out here is that you can look at the orbits derived in standard kinematic models, kinematic potentials as shown in the blue, and in the pulsar accelerations that are shown in the red. And they can be quite different because the mass distributions that we're inferring are somewhat different from the kinematic potentials. How much time do I have left?
5 minutes exactly right now.
Okay, I think we can do this 5 minutes. Okay, so far we've used binary pulsars, which is the most rigorous way of doing this, but this does exclude pulsars that are not in binary, so we wanted to see if we could take advantage of solitary systems as well. So I'll just remind you, this was how we derived accelerations from binary pulsars. That is, we have the observed period drift rate, and we have the physical mechanisms that lead to the observed period drift rate on the right-hand side. We know everything on the right-hand side here, so we can isolate and solve for the galactic acceleration. And you can write down a similar equation for the time rate of change of the spin period, but the difficulty here, and this is why we didn't do this initially, is that now you have this very notoriously unknown magnetic braking term. So these pulsars have strong magnetic fields, they pump away angular momentum, and even the nature of this magnetic field is unknown. Now you can make some progress here if you realize that the line of sight galactic acceleration is equal to the line of sight galactic acceleration, whether you express it in terms of the time rate of change of the spin period or the time rate of change of the binary period. And this one we know, okay? The time rate of change of the galactic galactic potential as determined from binary pulsars for the sample of 26. We now know that, so we can use that to determine an empirical calibration of the magnetic braking term. And this works quite well for low magnetic fields and large characteristic ages, which expands our sample of acceleration measurements to 54 sources and lets us study a wealth of disequilibrium features in the galaxy, okay, including, for example, this as a large Magellanic Cloud is moving towards the Milky Way, it leads to an offset between the disk and the halo. All right, I'm going to fast forward through some of this. Now, for the first time, we have an actual measurement here in the red of the local dark matter density to nearly 4 sigma. Okay, this is the first such measurement of the local dark matter density from direct acceleration measurements, which we were unable to do in previous samples because we just didn't have enough pulsars. And the blue here is showing the kinematic values. So now, our ultimate goal was always to see if we could understand the nature of dark matter. Okay, so we now have sensitivity, okay, with this expanded sample to subhalos, whether they are dark matter clumps or primordial black holes, I do not know, but we have sensitivity in this larger sample to objects that are of order 10 to the 7 solar masses. Okay, and what we've done here is we've gone through and searched for pairs of sources that show localized deviations from a smooth galactic potential that experience this in a correlated sense, that is, it is experienced by multiple pulsars at a minimum 2. Okay. And that's how we characterized this subhalo, or it could be a primordial black hole. It's of order 10 to the 7 solar masses. Okay, it's about a kiloparsec from the sun. The mass significance is not high. It's anywhere from 2 to 3 sigma. Base factors are of order 30. So it's tentative, but I will point out that the previous work on characterizing subhalos in the galaxy focuses on gaps in stellar streams that leads to uncertainties of order a couple of orders of magnitude. So that's, I think this is an improvement, but in the future, what we really want to do is to get constraints on the density profile. And as we start to pack this region, that's the subhalo, that's the sun, these are the pulsars we use. As we start to pack this region with more and more accelerometers, we should be able to determine the density profile of this object, whatever it is. In observable space, this is showing the fractional error in the observed line of sight acceleration relative to a model. That's for a model that doesn't have a subhalo. This is for a model that includes a subhalo. These colors are a little bit lighter, so maybe there's some tentative suggestion here. Let me skip over this, and I will go ahead and summarize. So, talked about our work and the discovery of a 9 solar mass stellar mass object from Gaia DR3. We have some initial characterization of an interesting object from pulsar timing. Of course, these accelerations are much, much lower than the stellar mass black hole accelerations. The stellar mass black hole accelerations I've been talking about are like tens of kilometers per second over several days or months. These accelerations I'm talking about are about 10 centimeter per second over a decade. So very different regime. I'm excited about the release of Gaia DR4 and potentially I'm looking forward to maybe discoveries of stellar, massive black holes and galactic outskirts. Hopefully that's a possibility, but I want to hear from the experts on this. And in the future, we certainly should expect a tighter constraint on this object, whatever it is. Thanks a lot for your attention. I'd love to take questions.
All right, thank you very much. We have time for questions. So Norbert first.
Yeah, thanks very much. Lots of exciting stuff. I want to comment on your idea that massive black holes, or even massive black hole mergers, can form the outskirts of disk galaxies due to their low metallicities there. So we have the long duration gamma ray bursts and also the superluminous supernovae, which preferentially occur in low metallicity regions in the nearby universe. Now those seem to mostly have host galaxies which are dwarf galaxies. So those are not found often in the outskirts of disk galaxies. Would that contradict your ideas?
No, not necessarily. I think there's, as you saw, there's some uncertainty in the numbers that we're getting. And of course, it's true that there just are more dwarf galaxies than there are big galaxies. Now, the other thing is that this way of getting the merger rate that I outlined, we made a number of simplifying assumptions there. One is we're assuming this average metallicity for outer H1 disks in the last 20 years, from Rob Kennicott's first work on M101's metallicity in the outer disk to more recent work that was done by Fabio Bressel, and those metallicities have increased a little bit, not a huge amount. They're still certainly subsolar, but they've increased a little bit. We used, back in 2017, we used the earlier value, so that's one thing. And as you saw, the mass efficiency, very steep dependence on what you assume about metallicity. We also assumed a constant star formation rate and, somebody's mass metallicity relation. So, there's lots of room for improvement, but to me, it's not a priori obvious that this is, that the outskirts of galaxies are a region where you couldn't form massive black holes, just because, as I said, there is, regions of low metallicity more easily form these very massive systems. So I think it's an area that deserves more research.
Can you pass the mic to Ilya? And reminder to introduce yourselves before speaking, please.
Ilya Mandel. So this 10 to the 7 roughly solar mass over density that may be a subhalo or primordial black hole, what volume can you constrain that to?
So what we did is we went through our entire pulsar sample. Okay, so I should have also said that we can rule out anything that is more massive than 10 to the 8th solar masses within several kiloparsec of the sun. And the accelerations, of course, how they scale with radius. So if you're looking at pulsars that are very far out from the subhalo, they're not going to help you. Okay, so you can say that it is constrained to better than half a kiloparsec of the distance that we're citing in that paper.
Thank you for the great talk. I have a question about the accelerations also. Every time I think about accelerations, I feel sobered that a measly M dwarf at 50 AU does more accelerating than the galaxy, right? So my question is, to which extent, of course, but distant low luminosity companions are random. To which extent do you know that that doesn't play a role? And then in turn, what constraints does that actually place on how often?
I missed the first part of your question.
Oh, M dwarf companions, far away out there, accelerate more than the galaxy. How do you know your pulsars are not just having a low mass object at 100 AU orbiting them?
Right, right.
Oh, Hans-Walter Rix.
Yeah. Thank you. Thanks for the question, Hans. Yes, that's right. So that is a possible contaminant. And, you know, when the pulsar timing facilities, Nanograv and others, release their parameter fits, they do include, and you can include, an additional companion mass like this. And in fact, as you know, there have been pulsar planets that have been found. Now, there will always be some level of uncertainty, especially for long period low mass systems. And in the paper, we talk about, and off the top of my head, I'm not remembering what are the limits on the mass and orbital period that we gave, but we give some limits on the mass and orbital period that we can now exclude. So that's in the appendix, but I'm off the top of my head, I'm not remembering that.
All right. Kareem?
Kareem Al-Badri, Caltech. For the 10 to the 7 solar mass object, is there a way we can like see the evidence for it in the data, or like what does the data look like? How many pulsars do we see evidence for it in? And yeah, kind of along one.
Right. So yeah, that's a good question. If you, for example, what I was trying to show in that plot with the fractional error is that you have a model that does not include the subhalo and a model that does include the subhalo. Okay, so in that case, maybe we can go back here. So this is a model this is the fractional acceleration, observed line of sight acceleration relative to a model, okay? This one does not include a subhalo. This one includes a subhalo. So it is marginal, right? These colors on the right are slightly lighter, but it isn't a significant difference. So at the moment, we only see the difference above the noise for a very small handful of pulsars, but the period drift rate uncertainty, okay, scales roughly with time as t to the minus 5/3. So that means that you can, as you're measuring accelerations, you can only get better with time, and you get better with time roughly quadratically. Okay, so this will get better with the Nanograv 20-year data release, and I didn't talk to you about the other techniques that we have to measure pulsar accelerations. So, which includes eclipsing double white dwarfs. In fact, the eclipsing double white dwarf system that we have been timing for several years now, which will be out next year, which has a precision in the period drift rate of about 6 sigma. That's comparable to binary pulsars. It's very close to that subhalo. So we will have more evidence for this very soon, one way or another, but 2 to 3 sigma significance, there's a decent chance that we're wrong.
I'm going to inject myself here very briefly. Carl Rodriguez, UNC, can you describe a little bit more the model that you used to compare against without the dark matter subhalo? Because I can imagine a lot of baryonic physics I could cook up that might do this as well.
Absolutely, yeah, this was a letter, and so we didn't do a very broad consideration of small-scale baryonic distributions. We did a little bit of this, and we considered a range of galactic potentials. This is shown here for an exponential disk. You could add a bar, but this is fairly distant from the bar, and if you know, it's a quadrupole going as r to the minus 4, right? So it's unlikely to have an effect. We have looked at the effect of spiral arms. That does not mimic this. And the important point here is this is distinct from the dwarf galaxy perturbations that I talked about earlier. Those give you asymmetries on several kiloparsec scales. Here, we are talking about highly localized deviation, less than kiloparsec scales, okay? The galactic acceleration in units of centimeter per second squared is about 3×10⁻⁸ in units of centimeter per second squared. That's this 10 centimeter per second per decade number, right? Now, this thing is about a few 10⁻⁹ centimeter per second squared. So we're just sensitive now to those type of accelerations, but these are highly localized deviations relative to a smooth potential.
Thank you. All right, Tina, then Tom.
Thank you. Martina Hrušnička. I would like to go back to the topic of massive stellar black holes and galactic places. So I think the galactic outskirts are probably a good candidates to look for massive stellar black holes forming now. But with black holes, we're often not looking at, we're not probing their formation epochs.
Right.
So overall, probably much more mass formed in central regions, and over the cosmic history, a lot of that formed at low metallicities. So perhaps a slightly different question is also an interesting one to ask, like, are the outskirts more interesting to look for those massive black holes relative to galactic centers, given the overall star formation history of galaxies of different masses?
Yeah, right. Yeah. So yeah, there's some, trade-offs, right? Of course, there's some regions that are going to form more, stars because the star formation rate is higher. But then you have the problem that, it's also enriching the interstellar medium and the metallicity is going up. And so they may not lead to very massive black holes that are more massive than.
The black holes stick around once they form.
You could have repeated, mergers. Is that what you mean, or?
No, once you produce a star-mass black hole, it sticks around, right? And it might be in different configurations with other stellar objects or compact objects. But with black holes, when we look at those systems that especially have low mass companions or are in merging systems, we're looking at the integrated cosmic star formation history. And also metallicity is an important parameter there, as you pointed out. Right. So overall, when we look at this integrated history, it's not obvious that the outskirts are still the interesting places to look at.
Yeah, so firstly, I'm not saying that they're the only place to look at or even the most interesting place to look at. And by the way, one other thing that I want to make a distinction about is that, I'm really thinking, at that time when we wrote the paper, right, this was, I'm coming from an astrostatistics workshop in Huntsville that some of us were organizing, and this is the 10th anniversary, right, of the LIGO detections. And at that time, I was really thinking about the detections of these really massive black holes, not the stellar mass black holes, but these really massive black holes, right? And we're using this mass efficiency model, right, from one of Chris Belchinski's earlier papers that is focused on this very mass event. So not things like IBH1 or BH2, but more massive than BH3. I don't know if that answers your question. Okay.
All right, and I think last question for Tom.
Tom Macaron, very nice talk. So I was thinking about your discussion about supernovae on the outskirts of galaxies, but yesterday we heard about disappearing stars as being a black hole formation channel. Has anybody done a search on the outskirts of nearby spiral galaxies for disappearing stars?
That's a great question.
And is somebody, if you don't know if somebody's familiar with the Ohio State project, knows how far out they go with those?
I don't know the answer to that. Does anybody else know?
Nobody? Okay, that's something for us to look up in the coffee break then.
I guess we've got a little bit more time.
Okay.
Really quick, because that was a quick question. Cheyenne Shariat. So if we have like a localized dark object that's very massive in that range, and within a kiloparsec we have 1 million wide binaries that are loosely bound and potentially sensitive to a disruption of a dark object going by them, do you predict that if we look at that location in the galaxy, let's say a few parsecs or 50 parsecs around it, we expect some different characteristics of the wide binary population, which is a very sensitive population, compared to another part of the galaxy that presumably does not contain a subhalo?
That is an excellent question. I mean, I've looked at binaries in double white dwarfs, and we're tracking those, but not in this kind of statistical demographic sense. So I'd have to, which is, I think, a really good thing to do. So I'd have to think about that more. It might, depending on how many you have and depending on how tightly the parameters are, it would really just depend on how precisely the parameters of the orbit are known in that region of the sky relative to some other region of the sky. And Karim is much more of an expert on that than I am.
Let's thank Sukanya again.
Thank you.